Hello, I'm Ben. I'm a PhD at Imperial College London, and I'm going to be talking about some testing that I've been doing recently on some reactor pressure vessel steels. This is particularly a nuclear application mainly. Reactor pressure vessels are a critical part in a reactor. When the pressure vessel goes, that's when the whole system's going to go. So where we're looking at extending the life or making sure that the systems run safely, safety critical components like that, it's very worth working towards understanding how they work, how they fracture, how they're going to end, so that we can continue to work on how they work, on how they continue to operate. Those sorts of areas then, if we're looking at ensuring the life of something safely, extending that life, we need to reduce previously over-conservative estimates on things like fracture toughness to ensure that they continue to operate safely. Two key areas then is the rate that those sorts of things are experienced, the strain rate experienced. High strain rates have quite a high area of uncertainty through testing. So reducing that, improving our level of conservatism required. And then also low temperature testing. Low temperature for me, meaning onset of upper shelf transition. Over time, this may be a high temperature, but for the material that I'm working with, it is a low temperature. So both of these areas, we're working on understanding them better to ensure that we're safely using these materials as they can do. Today, I'm going to be talking about certain Sharpie testing that I've been doing, so high strain rate at multiple temperatures, to see how our temperature changes with different sorts of materials, different sorts of geometric constraints with this reactor pressure material. If we're talking about then fracture toughness, that's where I'm going for with this. I've got a Sharpie to do it, but I'm talking about fracture toughness. If I talk about linear elastic approaches and I look at the typical standards for fracture toughness assessment, if I want to use linear assessments, I would have to have a very large sample. Difficult to test, very high levels of load required, and I can't put that in a Sharpie testing machine. If I go to linear plastic elastic assessment, the J-integral method, for looking at my fracture toughness, much better for my sort of material. This is an incredibly ductile material. And I get to an approximate sort of sizing that I'd need there to be more reasonable, but still not quite a Sharpie. I use some Sharpie testing. So this is where we come into calling these sorts of tests sub-sized or substandard tests. So fracture assessment here gets into the realms where validity is difficult for typical fracture mechanics. So where we're looking at validity there and small samples, we get geometric constraints and constraint effects coming in. Looking around that sort of thing, I've investigated three different sorts of constraints with my Sharpie size. So 10 millimeters, 10 mil by 10 mil by 55 mil. I've got low constraint, that's just the V notch, a typical Sharpie. I've got a medium constraint where I've pre-cracked by fatigue. And then I've also got a high constraint, which is pre-cracked and with side grooves on the side. Interest here there is how does this affect my ability to do fracture mechanical testing using these sub-size samples? The key areas that I've done so far then is Sharpie impact testing. So that's a high rate test. And the best sort of results I can show you are the energy requirements. So I have here absorbed energy for fracture. Very nice curve that we're getting with our very nice Sharpie machine. It's an instrumented Sharpie machine. So not only can I observe the energy required, I can also investigate the force and displacement histories from each of these impacts. So from a number of tests, we have the lovely traditional sort of Sharpie test transition curve coming to a good transition where we've got the fracture surfaces I've shown as well. These are for the notched samples, so the whole fracture surface went in one go after the notch. We have very classically brittle behavior transitioning to a very classical ductile behavior. Lovely. So that's the notch, that's the low constraint. We go up one level of constraint to the pre-crack system. So all of these have a very fine crack, showing the pre-crack face as well. Notice the energy value has massively reduced from the change in the A of W ratio, with the crack coming to 1/2 way instead of 20%. And we also have that transition. And finally, the highest constraint. We've been steadily increasing in brittle ductile transition by quite small amounts, granted, but it is increasing. So from -18 to -13 to -10. So it's increasing the transition temperature and reducing that energy requirement. It's quite nice. We've got some good testing out of there showing that the fracture energy required with our different constraints is reducing the amount of energy required, reduced toughness. For the same material, just changing the geometric constraint. I said before, this is an instrumented test, so I've also got force displacement data, and I can run through standard equations to then investigate and interrogate the geometrical method for fracture toughness through these as well. Oh yeah, here they all are together, just to show that they are coming down. Here we go, the force and displacement data. I've picked out one of my pre-crack samples that was ductile and was brittle. As we can see, again, very classical, brittle and ductile sort of behavior. We come up to a load and snap just right off from the brittle behavior, very nice. And then we're coming up and having some plasticity coming through. The little jump during the plastic region is very typical for plastic collapse, something that is very difficult to work on when we have small samples. Looking then through all that data, I can look at the force and the force history, and look at the geometrical for the toughness. This is then where we come into these sorts of tests for the different setups. Green, good. These were ones that lay quite well with validity testing, that these were valid tests. They ticked all the boxes required. They weren't fully plastic collapsed before we could observe the critical value for fracture. Red, bad. Plastic collapsed before it went down. So it's so ductile material, there's no useful data there. Orangey color is also bad. That's where we've gone to dynamic invalidity. That's where the system hasn't come to a good equilibrium to be able to do the classic geometrical method. We get inertial effects, and we get it doesn't come to an equilibrium before the force can go down. So the most brittle ones, the coldest ones, are the ones that went dynamically invalid. They snapped before any good data could be extracted. So it's quite a small range that we can actually get valid toughness assessments coming out through these small tests. Highlighting there the range in which all of them went through from that transition from brittle to ductile. The only one that's actually looking quite useful is the pre-cracked one, the one in the middle. So the side grooved ones, even though it's got slightly more valid tests where we talk about traditional fracture mechanics, the dynamic instability is coming into effect there. So there's even less useful data coming out of these tests. Useful range, green, is the area where I can be very happy with the sorts of tests that we've got, and that the standard methods of fracture mechanics come into effect. Final sort of areas there from this, then where can we go forward? One area that I'm continuing to go through is to extend this not just for Sharpie, but for the same size samples with the same difference in constraint, but for different rates. I can now show that there is a valid range where I can observe good fracture information and I can extract valid data. Is that range good within slower tests? Will a static test, it'll be better for a dynamic validity. Will the validity start to work in those areas? So I have static and intermediate mid-range as fast as my static system will go. I don't have full data to show for that. It's taking quite a while to go through all those numbers, but I can show you the fracture surfaces from a room temperature upper shelf where it should be very brittle, or it should be very ductile, apologies, to a low temperature, where it should be very brittle. And that's a nice area that is showing up. There's not much difference between the fracture surfaces. The Sharpies, we had plastic collapse, and it showed a very typical breaking apart, very typical ductile bending and plastic deformation. With the slower rates, it's starting to show and observe to be very similar between both sides of the transition temperature. So this is either an incredibly ductile material that is never going through true transition, or a material that's staying brittle all the time. It's definitely a ductile material. So the same for for the intermediate speed, so a bit faster than what is classified as static. It's definitely a brittle material. It's snapping through. This is the intermediate test for a pre-crack sample. So this is as it ran live sort of time scale, not sped up. It's pulling apart, and I can see, even just with the naked eye, we can see plastic deformation. So it's certainly breaking in a brittle mode. This is in the lower shelf. So this is minus 60 degrees Celsius. So it's still showing a ductile mode, even though we're in what my force histories and what the energy curve would expect to be brittle. Thank you very much for listening. Any questions?